So here we go. So share screen. I want to show you this screen. So we're going to be learning a lot about how I want labs to be written up in the lab notebook, and also some information that you would normally learn from the textbook or in lecture also, but I also use lab time to help explain that. So this is the measurements lab, and the first part of the lab tells you what you need to submit by the due date. So you can see that you're supposed to write it up in your lab notebook with a title, an introduction, safety, procedure, data, calculations based on the assignment that's below, and results like the area of the card, and then a discussion. You want to submit the following photos of your lab: the paper ruler on a scale so that the numbers on the scale are visible, the meniscus of the water in the graduated cylinder, the length of the card showing the store ruler next to the card so that the numbers on the ruler are visible. So you're going to submit 3 photos along with your submission for this particular assignment. And you're going to answer the questions at the end of the lab and submit answers. And so at the end of the lab, we have this assignment here, and these are the questions that you're going to answer. Ooh, I need to change that number 1 here. Let me go to an edit real quick. Boom, edit. And I'm going to scroll down here. And that does not need to be in bold, nor does it need to be bulleted. So we'll get rid of the bulleting. All right. So these are the calculations that you're going to be doing for this lab. And these calculations, since you're going to be doing them in the lab write-up, so to speak, for number 1, you can say, refer to the calculations in the lab write-up, and that would be perfectly fine. Okay, you'll understand more about what I'm saying in just a moment. So let me save this before we move on. Otherwise, the change I made won't be saved. So, good. All right, so make this a little larger. And let's take a look at the measurements. So when you write this up in your lab notebook, you're going to put a title down first, and the title for this one, measurements, is perfectly fine. The introduction tells you a little bit about what you're doing and what's important for the lab. And really, we need to read some more about this to know what to put in the introduction. So I'm going to skip that for just a moment and go to safety. You always write a safety section in your lab. If there are not any safety issues, then you write safety. There are no issues for this lab. The procedure, you describe what you're doing in the lab. And for the procedure, sometimes you like to have the procedure written ahead of time, but while you're doing the procedure, you're going to write it up in your lab notebook. And then you want a data section. Now, with the data, you want to collect the data in your lab notebook, and it's difficult to know where to begin the data section and where to end the procedure if you're writing the procedure as you're doing the lab, and if you're collecting data as you're doing the lab. So what you normally want to do is just leave enough room, more than enough room, to write the procedure down and then collect the data. And if there's leftover room in between, that's okay. So I'm going to skip calculations for the moment, results and discussion, and we're going to go to measuring. So what I'm writing here is how to measure things. And basically, I'm describing how you measure using a digital device and how you measure using an analog device. So I'm going to do a switch screen here so that you can see a digital device versus an analog device. All right, so here's my camera. This is a digital device. If I open this up and turn it on, you can see numbers in a digital format. So this is a digital device, and it's a balance. When you are using a digital device to measure things, you record all the numbers that you see on the device. This is the scale that I suggest that you buy. It only costs $15. And it's very handy. It measures things down to the 100th of a gram. Let me see if I can tilt this a little bit. You can see the G in the lower right-hand corner in the screen. That means grams. And you can see when I put a ruler on it, it says 6.76 grams. And so you write all of those numbers down. Now, apparently this is locked into place. Oh, no, it hasn't. I wonder if I can lock that. Is that what that means? Who knows what that means? At any rate, you write all the numbers down. Now, when we look at this number, 6.76, everyone believes the first 6. Everyone believes the 7, but that last 6 might not be a 6. It might be a 5. If I were to put this same ruler on another balance made by the same manufacturer and weigh it, it might be 6.76 grams. And you can see here, it just changed to 6.75. So should we write 6.75 or 6.76? And the answer is, I'm going to write down 6.76 because that's what shows up more often. But this ruler on another balance might read 6.75. On another balance, it might read 6.77. The important thing is that last digit might differ on different balances, but it will not differ by much. It's highly unlikely that if I put this ruler on another balance made by this manufacturer, that it will read 6.72. So that means that last digit is significant. That is, it is important and we want to record it. And here you can see it's an 8. Is 8 so far different from 6? No. So it is significant, it is important, we record it. So that's how you use a digital device. You record all of the numbers and you record the unit. Okay, so what is an analog device? This is an example of an analog device where you don't see any digits or electronic digits, but rather you read out based on the hands of the watch. This is also an analog device. There are digits on here, but it's not electronic. So this is an analog ruler. And when you're measuring with the ruler, what you want to do normally is you line up the 0 with one edge of whatever you're measuring, and then you read to the other edge. Now, let's take a look here. I'm going to zoom in on this number here. And you can see, I'll move this a little bit. You can see that the edge of the card looks like it matches up with the 3 very, very well. So what would we record as the number here? Well, if we wrote down 3, that means we're pretty sure it's a 3, but we're not certain, which means it could be a 3, a 2, or a 4. But we're absolutely certain that it's a 3. How do we convey that? Well, we would write 3.0. But if we think this is really on the 3, would we write 3.00? How many zeros would we write? And the answer is it depends on how confident we are that it's at the 3. But an additional problem with this particular ruler is that this over here is 3.5 in the middle, and over here this is 4 inches. The problem with this ruler is that the inches are not divided into even spaces of 1/10 of an inch. So if we were right here, what would we write? Let's see. If we were right here, we might want to write 3.25. Would that be appropriate? And the answer is, I have no idea. Now I'm switching the ruler around so that we're looking at the centimeter end. I'm going to line up the centimeter end with the edge of the card. So 0 centimeters, and I'm going to move the whole thing over. And now we're going to take a look at the other edge. Oh, I got to realign it. So the 0 is lined up. And what do we record for the length of the card? So I'm going to back it up, and I want to remind you that I am talking about how do we record using an analog device. So this is an analog device. Now, this number here, 7, is 7 centimeters. This number 8 is 8 centimeters. And you can see that this is divided into 10 equal spaces between the 7 and the 8. So that means that when you go to the line next to the 7, that's 7.1 centimeters, and then 7.2 centimeters, all the way up to here where it's 7.9 centimeters and then 8 centimeters. So can you see that the card goes past 7.6 centimeters, but it does not make it to 7.7 centimeters? Can everyone see that? If you can, give me a thumbs up in your little icon area. Excellent. Okay, so can you see that it's not quite halfway between 7.6 and 7.7, not quite halfway. When you're using an analog device, you make a guess as to how far it is. So do I think it's halfway? If I thought it was halfway, I'd write 7.65. If I thought it was close to halfway, I might write 7.64. And if I thought it was not so close, I might write 7.63 and so forth and so on. So what I'm trying to tell you there is you take that smallest little division there of 1/10 of a centimeter, and you decide what portion it is past that the 10th. And you do this in tens, or in, how many parts in 10 is it past? So if you take a look at this, some of you might say that's 7.63, and that's perfectly fine. Some of you might say that's 7.64. It's a little more than 6.3, and that's perfectly fine. So I'm going to write those values down here. If you wrote any of those values down, I'd say, you know what, that's good enough. And I think we would all agree that the difference between a 2, a 3, and a 4 is very small. So that means that this last digit is significant. So that's how you use an analog device. Now, in the procedure, it tells you, so I'm going to zoom out now. In the procedure, it tells you to take your ruler and make a paper copy of it. So just take your ruler, put it on a piece of paper, trace it. And here I'm going to put lines here at 0, 1, 2, 3, 4, 5, 6, all the way up to 15. And then I'm going to bring the lines down. And then I'll put a 0 here, a 2 here, a 4 here, and so forth. And I'll make a paper copy of my ruler. And it ends up looking like this. So can everyone see that, the paper copy of my ruler? Give me a thumbs up if you see it. Okay, so here are the two rulers, and you can see that they're pretty much the same thing. So now let's take a look at our paper ruler measuring the width of the index card. So I will zoom into this area. You can see that this end is lined up. We'll zoom into here. Okay, so what I want you to do is I want you to, based on what we can see here, and based on the understanding that we can measure to 1/10 of the smallest increment, I want you to think about what number we should write down here. Okay, so first of all, what is the distance between two adjacent lines? What is that distance? 1 centimeter. So we should be able to measure to 1/10 of 1 centimeter. So think about the number you would write down for the length of this card. When you have a number, give me a thumbs up. Now, when you give me the thumbs up, I'm not asking you what your number is. Just give me a thumbs up so that I know that you've thought about it and you have something written down so we can talk about it. Do you know where the thumbs up thing is, Rita? You open up your participants list, then you go to the bottom of that, and it might be in reactions, but you can choose a thumbs up. We'll go ahead and keep going because I'm sure you'll find it soon enough. So can everyone see that the card goes past 6, past 7, but doesn't go to 8? So we're going to write down 7. And it looks like it goes more than halfway past 7 to 8. So I might write 7.6 centimeters or 7.7 centimeters. I don't think I would write 7.8 centimeters, and I certainly wouldn't write 7.5. But these are the two values I might record for the width of this index card. If you have any questions, now's a good time to raise your hand and ask. Or if you don't have any questions, then we'll just move on. Is everyone okay with either of these two measurements? Is everyone okay? Give me a thumbs up if you're okay. Okay, we're going to move on. Now, what if you're using another analog device? So this is another analog device. This is a graduated cylinder. Now, I'm going to warn you, I have my graduated cylinder laying down on my desktop. These are not meant to be used this way. They're meant to be used standing up. But it's much easier for me to show you what's going on with a graduated cylinder if I lay it down. Now, if we take a look at the numbers, you can see we have 100, 90, 80, 70. On the other side, we have 0, 10, 20, 30. If we want to know how much liquid is in the graduated cylinder, we obviously want to use this side because this tells you how much is in there. Notice at the top, it says milliliters. So whenever you're using a measuring device, you always look for the unit. This is in milliliters. So this is 100 milliliters. This is 90 milliliters. I'm going to move this down and zoom in on this. Okay, so I've zoomed in on it. How many spaces are between the 90 and the 100? And the answer is there are 10 spaces. So that means each space, each division must be 1 milliliter. If each division is 1 milliliter, we should be able to measure to 1/10 of that. 1/10 of 1 milliliter is 0.1 milliliter. So we should be able to measure to 1/10 of a milliliter. All right. Now, when we are measuring a fluid, what do we actually measure? Well, I'm going to show you a little drawing here of what you would actually measure. So I'm going to scoot this over a bit, and I'm going to draw a graduated cylinder. And so here's a 90 and here's an 80. And I'm going to break this up. And when you're looking at liquid in a graduated cylinder, this is what you actually see. You see a little bit of a bow from the water. This part right here, which is the lowest part of the water, is called the meniscus. And the reason there is a meniscus is because the water is actually attracted to the glass of the graduated cylinder. So it's kind of crawling up the sides of the graduated cylinder. Since the graduated cylinder is not in the middle of it, the water doesn't climb up. So this is a very simplistic drawing of the graduated cylinder, but you have to imagine that it's not only climbing up here and here, but it's also climbing up at the front of the graduated cylinder and at the back. So when you look at this, it looks kind of complicated. And you're supposed to be able to read to the bottom of the meniscus. Now, based on my drawing here, can everyone see how that meniscus is pretty close to 83? But we should be able to guess how far past 83. I might put 83.1 milliliters based on my drawing. Okay, because it's a little bit past 83, but it's not right at 83. What if it were right at 83? What would we write? We'd write 83.0 because the 0 is a measurement. Are there any questions about looking at the meniscus and how to read a volume in a container? Any questions? Are you okay with this? All right, Rita, you found everything. Excellent. Is everyone okay with this reading here? Let's go to the internet and take a look at a photo of a meniscus, okay? So I'm going to change my share to this. So this is the lab that we're looking at. And I'm going to write graduated cylinder meniscus. This morning when I put this in, I just wrote meniscus and I got a bunch of knees. Okay, so here we have these images of graduated cylinders. And here is the simplistic drawing of the graduated cylinder. Can everyone see the meniscus here? So based on the idea that each one of these is milliliters, I want you to write down what you should record for this meniscus. When you have a number written down, give me a thumbs up and then I'll show you what number I would have written down. So give me a thumbs up or a check mark once you have an idea of what you would write down. Okay, so let me tell you what I would have written down. I would have written 24.0 because I think it's right at 24. If you don't write 0.0, that means that the 4 part of 24 is wishy-washy. So I'm going to switch my screen back to the tabletop here. So if we had written for that particular drawing 24 milliliters, we know that the last digit is wishy-washy like the balance. So this could really be 23, 24, or 25 milliliters. Or at best, it means it's 23.5 to 24.4 milliliters, because 23.5 would round up to 24 and 24.4 would round down to 24. So that's what this value means. But if we think it's right at the 24, we have to put 24.0 because this at best means that it could be 23.95 milliliters to 24.04 milliliters, because this would round down to 24 and this would round up to 24. And I think based on the image we saw, this is more appropriate. So if you think it's right at the line, you put a 0. Also from that drawing, so I'm going to draw it again here, we had a 20, we had a 30, and we had nice even divisions here. And it was right there at that 24. So here, if the smallest division is 1 milliliter, you measure to 1/10 of 1 milliliter. So that means you measure to here. And it could be 0.01, 0.02, 0.03, it could be 0.0. So if you're okay with that, give me a thumbs up. Okay, excellent. Now, let's take a look at an image of a real meniscus, because that's what you're going to have to do. So I'm going to switch here to this again. And I'm going to go back to the images of the graduated cylinders, and let's take a look at this one right here. Okay, so do you see the image at the top says ml, so that's milliliters. And you see the 100, the 90, and the 80? I want you to tell me what you would record for the volume in this cylinder. And now we're looking at a real meniscus, and you see it's not as easy as the cartoon drawing. So once you have a value, give me a thumbs up and we'll move from there. Trying to make it a little larger for you to see. Now, this is a chance for you to practice. You don't have to put yourself out there, because I'm not asking for your number. I'm just asking you to write a number down. You don't have to show it to anybody. And then I'll tell you what I would have written down. Okay, so if this line where can everyone see my cursor? Give me a thumbs up if you can see my cursor as I move it. Excellent. So this is 80. That means this is 81, 82, 83, 84, and 85. It is clearly past 82, but not 83. So my first two numbers are going to be 8 and 2. Now, how far past is it from the 82? So I want to go to the bottom of the meniscus here, and it is hard to see where the 83 is. But because I have the image on my computer pretty well, and I can see where the 83 is pretty well, to me, it looks like I would write down 82.7 milliliters. Okay, that's what I would write, 82.7 milliliters. Now, what should you consider to be a success on your part? Well, certainly if you wrote 82.7 milliliters, if you wrote 82.8 milliliters, I think that's a success. If you wrote 82.6 milliliters, I think that's a success. But I think the meniscus is more than halfway past 82. So 82.5, I think, would be close, but you want to do better. And because it's clearly underneath 83, if you had written something like 83.0, I think you need to improve that. So are we okay on the measurement there? Give me a thumbs up if you're okay with that. Excellent. Okay, so that's another analog device. In general, how do we measure using an analog device? So I'm going to say it, but I'm not going to write it down. And the reason I'm not going to write it down is because I want you to write it down. I want you to put it down in your own words, because it'll be more important when you write it down in your own words. So here's what you're going to do. For an analog device, you find out what is the measurement between two adjacent lines. Once you find out what that measurement is, you measure to 1/10 of that value. So if two adjacent lines are 1 meter apart, what do you measure to? You measure to 1/10 of a meter. If those two lines are a nanometer apart, what do you measure to? 1/10 of a nanometer. Now, I'm going to be honest with you, that's quite impossible because you can't see anything that small. Okay? If the two lines are a centimeter apart, you measure to 1/10 of a centimeter. If the two lines are 1/10 of a centimeter apart, oh, there's a tricky one. What's 1/10 of a centimeter? And the answer is you multiply 1/10 times 1/10, you get 1/100th. So 1/10 of a tenth is 100th. What if the two lines are 1/100th of a centimeter apart? You measure to 1/10 of a hundredth, which is 1,000th of a millimeter, which is really tough to do, I'll be honest with you. So in general, you measure to 1/10 of the smallest unit or increment or division, however you want to phrase it. Okay, that being said, I'm going to go to the document for the lab. Okay, so all of that stuff I just talked about is right here under measuring. And then we have the learning objectives, which basically say we're going to learn how to measure mass, volume, and length. We're going to learn how to round after an algebraic operation. We're going to learn how to convert, and we're going to learn how to write things in scientific notation. We've covered enough material to talk about what you would put in your introduction. So in your introduction, which I would use bullet points, I would say, well, we're going to learn how to measure mass, length, and volume. We're going to practice using algebra on these numbers. And we're going to learn the conversion factor method. And we're going to practice scientific notation. I'd put all of that into my introduction. The next section, which is the safety, and you might want to elaborate on the introduction. You might say, and we're going to do this by measuring things. What are the safety issues for this lab? Well, there aren't any. There are no significant safety issues, so you would write that. Never leave a safety section out of your lab write-up. Always put it in there, because if you leave it out, you're going to lose points. What is our procedure? Well, our procedure, if we scroll down, we can see that we're going to have to do the following. You're going to have to take your store ruler and make a paper ruler. You want to take an index card and you want to measure the length and the width with the store ruler. Measure the length and the width with your paper ruler. And finally, next you want to measure each ruler in grams. Put some water in your graduated cylinder. And normally for the graduated cylinder, I like to fill it about halfway. Measure it. And then you want to find a beverage container. Now, earlier this morning, I showed everyone this beverage container, nasal spray. If you look at the bottom, it actually says 1 fluid ounce is 30 milliliters. And the joke is that this isn't really a beverage. But you want to find a liquid container that reports the volume in ounces. It's usually fluid ounces and in milliliters. And you want to write that down. And you want to find a store product that has the mass in grams and ounces. And store products that normally have these things in grams and ounces are things like canned foods, candy bars, power bars. Those often have food in grams and ounces. Basically, anything that's a solid, it'll give you grams and ounces. Anything that's a liquid, it'll give you fluid ounces and milliliters. So for 6, find a liquid. For 7, find a solid. And I'm talking about a packaged liquid or a packaged solid. So are we okay with the procedure that you're going to do? Give me a sign if you're okay with that. Okay, so we're going to move on. Now, let's talk about the data that you would collect. For number 1, is there any data to collect? Give me a yes or a no. Procedure number 1, any data to collect? And the answer is no. Number one, make a store ruler or use the store ruler to make a paper ruler. There's no data to collect. Number two, is there any data to collect? Yes or no? And the answer is, yeah, we're going to measure the length and the width. Now, number three, is there any data to collect? And the answer is yes, the width and the length of the card. How might you write this data up in your lab notebook? Well, you might very well do something along the lines of this. Let me see if I can do this. You might do this: length, width, index card, store ruler, paper ruler. And here I'm going to put centimeters here, and I'm going to put centimeters here, because whatever value I put down here, it's going to be in centimeters, and here it's going to be in centimeters, and here it'll be in centimeters, and here in centimeters. So you might want to have a little data table with all of that information. And if you wanted to, you could even put in some extra lines. Okay, so I'm going to go back to the document that we're looking at for what to do. Okay. Now, let's go to 4, 5, 6, and 7. You can see that each of those, you're going to have to write down information or data. Okay, now let's look at the assignment. I need to change that. Let me go in and edit this. I thought I edited this just a moment ago. So edit. So I want to take this and I want to change it from a bullet to non-bulleted. And then we're going to go down here. And I'm going to save it. Okay, so for the assignment, I want you to determine the area of the card. So I'm going to use some measurements that I found this morning. I'm not sure if they're quite accurate, but you want to determine the area of the card using measurements from the store-bought ruler. So I'm going to switch screens now to the paper that I'm writing on my tabletop so that you can see what I'm about to write. Okay, so this morning, we found that the length of the index card was 12.73 centimeters, and the width was 7.62 centimeters. Now, when we used a paper ruler, we only got 7.6 centimeters for the width, and we got 12.7 centimeters for the length. So this is the store ruler, and this is the paper ruler. Okay, now to calculate the area, you use length times width. So this would be 12.73 centimeters times 7.62 centimeters for the store-bought ruler measuring the length and width of the index card. When I plug this into my calculator, 12.73 times 7.62, I get 97.0026. And I need the centimeters, but since I have two of them, it's centimeters squared. So this is what my calculator puts out as the answer. So the question is that my answer? And the answer is no, it's not. So to understand what we should actually report, and what we should actually report is this. To understand why this is the answer, we need to understand a few things. We need to understand significant figures. We need to understand carrying significant figures through algebraic operations. And we need to understand rounding. So we're going to go over all three of these very quickly because you've already discussed this in your previous chemistry class. So let's look at the rules for significant figures. And what we're trying to address here is this simple question: is it significant? So the first thing I'm going to tell you is that if it's not a zero, it's significant. So if I say 123 centimeters, that has three significant figures. My abbreviation for significant figures is SF. We have three digits here. None of them are zero. They're all significant. Three sig figs. If I have, we'll leave that off. Are you okay with the first rule? Give me a thumbs up if you are. Or yes. Okay, second rule. Tweener zeros are significant. So when I say tweener zeros, if we had 103 centimeters, that would be three significant figures. If you had 1,003 centimeters, that would be four significant figures. So what's a tweener zero? It's a zero that is in between two digits that are not zero. And the zero does not have to be next to a non-zero. It just has to be between, somewhere in between two non-zeros. If you're okay with this one, give me a thumbs up. Excellent. 3, trailing zeros with a decimal are significant. I want you to think back to that one problem where we read 24.0 milliliters. That's a trailing zero. When I say trailing zero, I mean zero to the right of the number. So that's a trailing zero. There's a decimal. This is three significant figures because we saw that that was 0 milliliters, not 0.1, not 0.2. It looked like it was at 0. That's significant. Now, how many significant figures are here? And the answer is 3 significant figures. That 0 is also a trailing 0 because it's to the right. And there's a decimal, 3 significant figures. Are we okay with the third rule? Okay, the next 2 rules are they're not significant. For leading zeros are not significant. Does this say anything about whether you have a decimal or not? Leading zeros are not significant. Doesn't say anything about a decimal because decimals don't matter here. Let me give you an example. 23 millimeters has 2 zig figs. There's no 0 there, so it doesn't really seem to fit. Now watch what happens. Is the number I have written the same size as the written number above? Are these 2 numbers the same amount? If you think they are, give me a yes or a thumbs up. And they are the same size. I mean, if I had to put a number here to the left of this 0, I'd put another 0 and another 0 and another 0. I'd put zeros out to infinity, and it doesn't change how much or how big this number is. It's 23 millimeters. So those zeros seem like they shouldn't count, and they don't. Are you with me there? Is everyone okay with leading zeros are not significant? Okay, now in a moment, I'm going to turn your world upside down. I'm going to rewrite this number. Your world should still be right side up. That is 2.3 centimeters, 2 zig figs, and it doesn't matter how many zeros I put in front of it. Now, I want to tell you something about 23 millimeters and 2.3 centimeters. They're the same amount. So if I measure something as 23 millimeters and I convert it to 2.3 centimeters, it still only has 2 significant figures. It's not hard to believe that that only has 2 significant figures. You can see where this is leading. 23 millimeters is the same as 2.3 centimeters, is the same as 0.23 decimeters. They're all the same value. Does it make sense to you that if they all come from this initial value, that they all should have the same number of significant figures? Does that make sense? I'm going to convert it one more time, but this time I'm going to convert it to meters. This is the same size as that. How many significant figures are here? And now your world has been turned upside down because you'd say, well, what about that 0? Doesn't it count? No, it doesn't count. It's a leading 0 and it's not significant. In fact, I can write this number this way. And I can put 4 zeros in front of the 2, 3, make it kilometers, and it's still 2 significant figures. Scientists found out long ago that just by changing the unit, it doesn't help to change the number of significant figures. It makes things worse. So we don't change the number of significant figures just because we're changing the unit. And so that means all leading zeros are not significant. So this may be a rule that you may not like, but you still have to be able to apply it. It's a rule that a lot of people don't like because of this. So what's the rule for leading zeros? They're not significant. The last rule is trailing zeros. We've already done trailing zeros with a decimal. So what are we going to do now? Trailing zeros without a decimal are not significant. So if we write 4,200 centimeters squared, that's two significant figures. Trailing zeros, no decimal. Now that doesn't mean we don't know where the decimal is. We know where it is. It would go after this last zero. But the fact that we don't see it means that these zeros don't count. Now, what would happen if I wrote down this? How many significant figures here? Well, we have trailing zeros with a decimal. So how many significant figures here? Go ahead and answer that in your head. And the answer is 4 significant figures. So these are the rules for, is it significant? Now we need the rules for carrying digits through calculations. So we have a rule for multiplication and division. It's the same rule. The answer has the same number of significant figures as the beginning number with the fewest. So I want you to recall that we multiplied for the area 12.73 centimeters times 7.62 centimeters, and we got 97.0026 centimeters cubed. So let's apply the rules here. How many significant figures in 12.73? And the answer, 4 zig figs. How many in 7.62? 3 zig figs. Which is the fewest? 3. How many are we allowed in our answer? 3 zig figs. Now, to actually report this answer correctly, we need to learn about rounding. So let's talk about rounding. Here, we want to keep the larger numbers. And when I say the larger numbers, I don't mean keep a 9 instead of a 1. I mean keep the numbers to the left. So this 9 means more than this 6, not because it's a 9, because it's farther to the left. So if I want to keep 3 numbers, I want to keep the 9, I want to keep the 7, and I want to keep the 0. Now, how does the rest of this number affect my answer? Well, once you figure out where you need to round to, once you figure what you want to keep, you look at the number to the right. and for that number to the right. If it's 4, 3, 2, 1, 0, you round down. If it's 5, 6, 7, 8, 9, you round up. So based on this, the number to the right is a 0. What do? We round down. So how do we round this number down? We take off these last 3 digits and we get a number that's a little bit smaller than what our calculator has. But this is the correct number to report, 97.0 centimeters cubed. 3 significant figures because of the 3 here. The 0 stays a 0 because that's a 0. Are you guys okay with rounding? Okay, let me show you another rounding thing. Let's say that we get this 14.49 centimeters squared. Should this be, if we need to round to the ones, should it be 15 centimeters squared or 14 centimeters squared? So think about that for just a moment. Make a decision. You don't need to tell me your answer. And then I will show you the correct answer. Okay, have you made a decision? Okay, now when I say to the ones, this is the ones, this is the tens, this is the 10th, and this is the 100th. And then of course you have thousandth, 1,000, 10 thousandths, 10,000, and so forth and so on. But I just want to talk about these. So some people think that this is what you do. They think that the 9 makes the 4 into a 5 because with the 9 you clearly round up. And then the 5 makes the 14 a 15, and they think that that's correct, and it's not. Here's how you do it. If we're going to round here, we look just at that next number. It's a 4, so this is 14 centimeters squared, and this is correct. So why don't we do this serial rounding? And the answer is because it's like a serial killing. It's bad. You're not supposed to do it. Okay, that's not the real reason. Let me show you the real reason why we don't serially round. So 14.49 centimeters squared goes to 14 centimeters squared. And I'm going to show you exactly why that is the case. This part here, remember, this is hundredths, right? So this means 49 hundredths. That's what that means mathematically. So I'm going to ask you a very simple question. Is 49 hundredths less than half or more than half of 100?
Less.
49 is less than half of 100, so you round down. We don't care what this digit is. If it were an 8, you'd round down. If it were a 7, you'd round down. If it were a 0, you'd round down. So we don't care what the next number is. And here, if it were 14.50, 0.50 means 50 out of 100, which is halfway. Now here you might argue, well, if it's halfway, shouldn't we round up sometimes and round down the other times? And the answer is yeah. Well, what's the likelihood all the rest of these numbers are not 1 or 2 or 3? Because if this is a 1, that means 501 out of 1,000. Is that more than half or less than half? More than half. What if this were a 0 and this were a 1? That would be 5,001 out of 10,000. More than half or less than half? More than half. So you can see that if you have a 5 here and a 0 here, the only time you'd really ever want to decide, well, maybe I should round up or round down, is if you have zeros forever here. What's the likelihood of that? About 0. Okay, so I'm hoping that now you have a better understanding of why we only look at the next digit and we don't care about all the others. Are you okay with that? Give me a thumbs up or a thumbs down, or give me some sort of feedback. Okay, excellent. Okay, so we were talking about carrying significant figures through operations. So what is the other most type of operation you're going to do other than multiplication and division? And the answer is addition or subtraction. So what is the carrying significant figures through addition and subtraction rule? For this one, we need to talk about an idea called precision. So there are two definitions of precision. One definition of precision is how close measured values are to one another. Basically, smaller range, more precise. So if we have 3 values collected and one person gets 1 centimeters, 2 centimeters, and 3 centimeters, and another person measures the same thing 3 times and they get 1.5 centimeters, 1.6 centimeters, and 1.4 centimeters, which set is more precise? And the answer is this is more precise. The range is from 1.4 to 1.6. And here, which is less precise, the range is 2 centimeters. That's more precise. If you think about it in terms of addresses, if you give me a street and an address on that street, that's more precise than just saying, oh, I live on W Street. But if you give me an actual number on W Street, that's more precise. Are there any questions about this idea of precision? Yes or no? So I'm asking you another skill. Can you put no down? Find the no. Okay. So this is one way to look at precision. Another way to look at precision is what is the smallest part of the number? Smaller is more precise. So if we have 12.72 centimeters compared to 12.7 centimeters, this is precise to the hundredth. And this one is precise to the 10th of a centimeter. So this is precise to the 100th. This is precise to the 10th. So this one is more precise and this one is less. So this is another way to look at precision, is you don't have a number of different values, but you just have one with that plastic ruler and you have one with the paper ruler. So which one's more precise? The one where you know numbers farther to the right. Any questions about looking at numbers and deciding when you're comparing them side by side, which is more precise? Any questions there? Okay, so what I'm going to do now is I'm going to ask you something based on this idea. Which of these two numbers is more precise? Come up with an idea. And once you have an idea, give me a yes, I have an idea. And then I'll let you know which one is more precise. Okay, so I'm going to tell you the answer. They're the same. And I purposefully tried to trick you. I tried to make you think that the one on the left is more precise because there are 3 numbers after the decimal, whereas this one only has 2 numbers after the decimal. Here's the trick. That's centimeters and that's decimeters. You don't get to compare apples and oranges. It's kind of like saying 1 inch is the same precision as 1 foot because you have a 1 for each of them. But an inch is much smaller. 1 inch is more precise than 1 foot. If we convert this to centimeters, we get 12.272 centimeters. And therefore, they're the same precision. So what am I trying to teach you here? I'm trying to teach you is this idea. When looking at precision, have the same unit. So do you understand that idea? To compare precision when you're looking at 2 numbers, they have to be the same unit. And that's why it worked here. They were both centimeters. Are we good on that? Excellent. So let's say we were to add 2 numbers together, like 12.72 centimeters and 12.7 centimeters. We're going to add these together. What is the answer? Well, there's no number here, but we pretend it's a 0, so we put a 2 there. 7 plus 7 is 4, carry the 1, put the decimal down. That's a 5 and that's a 2. So this is the answer when we add those 2 values together. But this is good to the 10th. This is good to the 100th. And here's the rule for addition and subtraction. So we didn't actually tell you the rule. So here comes the rule. For addition, subtraction, the answer has the same precision as the beginning number that is the least precise. So if we look at the above, this one is more precise. This one is less precise. So we need to round our number to the 10th. So if we're going to round to the 10th, we keep the 2, we keep the 5, we keep the 4. What are we going to do to the 4 because of the 2? Are we going to round up or down? And the answer is round down. And there you go. So that's how you carry significant figures through operations when you're adding and subtracting. Okay. Let's go back to the lab. We're almost done here, actually, which is good because it's 2:30 and we should be quitting here. So I'm going to go back to the actual document here and try and wrap it up. So here, I told you how to round so that you can learn how to do these problems correctly. I don't have any problems here with an addition and subtraction, but we'll add some more problems in there that have addition and subtraction in future labs. But you can see here what we're looking at. There is one more thing I want to show you, and that is, can you see number 4 says, convert the area of the card into square inches using the store ruler measurements. And don't measure the card in inches and use those values. Use your centimeter measurements and convert. I want to show you how to do that. This will take about 2 minutes. So I'm going to do a new share here. So we're going to convert 97.0 centimeters squared to inches squared. Now, to be able to do this conversion, we need to know that 1 inch is 2.54 centimeters. Now, this is defined. So that means that this has infinity significant figures, and this has infinity significant figures. Now, if I write 1 foot is equal to 12 inches, I think you'll all agree with that. And you agree with it so much that I'm going to write it down twice. Now, I'm going to divide this side by 1 foot, which means I have to divide this side by 1 foot. That's like the cardinal rule in algebra. The cardinal rule is if you divide one side by 1 foot, you got to divide the other side by 1 foot. In other words, what you do to one side, you better do to the other side. So here we get 1 is equal to 12 inches over 1 foot. I'm going to do the same thing over here, except I'm going to divide by 12 inches. And I get 1 foot over 12 inches is equal to 1. Now, the cardinal rule in algebra is what you do to one side, you have to do to the other. The cardinal rule in math is the identity law. It's such a big rule that they call it a law. The identity law is simply this. If you multiply anything by 1, you get the same thing. That is to say, if you multiply 5 by 1, you get 1. If you multiply 15 by 1, you get 1. And the rule goes a little further than that. It says if you divide anything by 1, you don't change it. 5 divided by 1 is 5. 15 divided by 1 is 15. So you can multiply by 1 without changing the amount. You can multiply by or divide by 1 without changing the amount. How many feet in 24 inches? Obviously 2 feet, but let's mathematically prove it. I'm going to multiply this by 1, and I won't change the amount. And this is how we do it. Do you see how this is equal to 1? 1 foot over 12 inches. So I'm multiplying by 1. The inches cancel. 12 goes into 24 2 times. 2 times 1 is 2. 2 feet. This is the mathematical proof that 24 inches is 2 feet. We can do this in our head, but this is how we mathematically prove it. Now, how does that apply to this over here? Well, I have this that I can use. So I'm going to multiply, and I'm going to put the 2.54 centimeters in the bottom, and the 1 inch on the top. And I'm putting this on the bottom because I want it to cancel with this. But there's centimeters squared here, and this is not centimeters squared. So what do I want to do? Am I allowed to do this? Is that okay? And the answer is no. It's not okay. This is roughly 1 inch and 1 inch. This is roughly 1 centimeter squared. This is 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 another centimeter squared. This is another centimeter squared. There are about 6 of these in here, 6 square centimeters in a 1 inch square. So this can't be right. So what's my workaround here? I multiply by 1 twice. This centimeter and this centimeter cancel with these two. You get inches squared. Since these have infinity zig figs and this has 3, how many significant figures are we allowed? 3. So I'll leave that for you to fill in, but that's how you convert when you have area to another type of area. How would you convert volume to another type of volume? And the answer is you do this 3 times. Okay, that's it. That took more than just a couple minutes. That took about 6 minutes. On Thursday, no, this is Thursday, right? On Tuesday, we'll be doing the density lab. Tomorrow, we'll be doing more lecture material. Glad you could make it. So unmute yourself and say goodbye to everybody.
Hi. I actually have a couple questions.
Oh, you do? What are they?
Yeah, so I was wondering for like our materials, our graduated cylinders and stuff like that. Are
Yeah.
we supposed to message you about picking them up or
No,
getting them mailed or?
you were supposed to sign that waiver.
Yes, I did.
So I just sent the addresses to my person who sends out the lab kit.
Okay.
The graduated cylinder you're supposed to have purchased.
Okay.
The balance you're supposed to have purchased.
Okay.
And the ruler you're supposed to have purchased.
Right. Okay.
But you're going to be sent other materials that you'll need for Thursday's lab.
Okay.
So if you sent me if you sent me your address, it just got posted today. The lab technician will either mail things out today or tomorrow. And if you're local, this is coming from Eureka, so it'll get to you next week.
Okay.
Okay.
Sounds good.
Now,
Yeah.
you said you had a couple of questions. That was one.
Oh God, I don't remember my other one.
Well, you can always email me if you wish, and I will try to respond to you.
Okay, sounds good. Thank you.
Was that Maddie that was
Yes.
asking the questions?
Yes. Hello.
Okay, Maddie, great.
It's nice to meet you.
Nice to meet you. All right, everybody. Toodles.
Awesome. Thank you. Bye.
Bye, thank you.
Okay, so I also had so I live in Sacramento, so I don't
Yep.
know when they're gonna arrive. So by the time you guys are doing it next week, and if it doesn't arrive, what should I do?
I'm sure it will arrive by then. I've had stuff posted to me from Southern California, and it gets here in about 4 or 5 days.
All right.
So if we get it out by Friday, which should be the latest we get it out, I'm certain it'll be there by next Thursday.
Okay. All right. Thank you.
Now, for the labs that we're doing today and Tuesday, these are materials that you should have purchased.
Okay.
All right, Rita?
All right.
Okay, Sacramento. Why are you taking a class so far away?
Oh no. I actually used to live in Eureka, but then my
Oh,
parents.
that would explain it then.
So
Okay,
with the pandemic going on, is pretty much my parents, they just want me to move back in, save money.
and be safer.
Yeah.
It makes sense. I would do that with my kids also. Okay, well, thank you for attending.
Bye.
Bye-bye.